the group that has assembled here. I'll just stand here so that there are several people online. They can listen to me then. So a group of faculty researchers have really gotten together here and all working in the areas of particle science, mainly aerosols in the gas phase. And we are quite a new group. So I'll just highlight some of the things that we are doing. And over the next 2 days, hopefully you get an exposure through our students and to the exciting things that are happening. And we, of course, want to learn from all of you. So we call ourselves the Center for Aerosol Science and Engineering, CASE in short. And basically it's pretty much in line with the theme of this workshop, physics at multiple scales. Of course, this is impacted by chemistry, right from the initial scales all the way to the sort of macro scales. And then we want to impact applications. Before we do that, we have to move these particles around, maybe deposit them, or if we are interested in examining a health effect and so forth, we also need to understand the same. So there are two sort of parallel streams. We try to piggyback on each other's expertise and are bringing this group together. So in terms of, we start, of course, with the molecular state. The key is to look at multiple species. So in any, let's say, an engineered system or maybe an atmospheric environment, there are multiple species, starting with the molecular phase. So if it's in the atmosphere, it could be formed by primary emissions or indirect chemical reactions, or in a combustion environment, or an intentionally designed high temperature environment where I want to end up with a desired product. I start with a bunch of molecular species. Then, of course, we study cluster formation and growth, the initial stages of these particles coming together. Many exciting challenges in that, many unknowns, and we'll, of course, hear grand challenges from you folks as to how we can sort of understand these initial stages and the importance of the initial stages, maybe all the way to the end in terms of the application. So multi-component clusters, how do they come together and so forth. And there are individual faculty or groups of faculty even here working on these different problems. Then, of course, the growth, now you go into more of an aerosol mode. Of course, these clusters are also gas borne and so forth. You can use the conventional terms, condensational growth. Now you form larger particles. So however, these particles could be multi-component, and in our systems, as I indicated, intentionally multi-component or inadvertently multi-component, which complicates these different growth processes. And then, of course, the movement, if there are inadvertently produced in a system, I might want to capture and prevent the release, or I want to intentionally deposit it, or I might want to intentionally produce a powder and so forth. So we do a lot of work in immobilizing these particles, understanding the fate and so forth. And you can see different shapes, different multi-component species, different decorations, morphologies, and so forth. So all of these, we sort of bring a bunch of faculty together using these fundamentals to enable applications. And our field, of course, aerosol science and engineering, is very exciting. A lot of importance in climate and environment. Environment, of course, could be in even monitoring the environment. So sensing, I can intentionally make systems to sense particles. Of course, particles in the environment have a role on health. I can make advanced materials, medicine. There's a lot of implications in producing pharmaceutical products or the fate of particles in a human system. Then, of course, enabling energy applications. And these are all, of course, grand challenges. Agriculture, this is agricultural land, the Midwest. We, of course, have plentiful water, but could we do this in a more efficient manner? And then even a routine commodity powder, where we make these particles in large quantities for sort of even routine application. So it's a tremendous group that comes together here, and I list some of the faculty researchers. I'll just highlight the laboratories rather than read out each name. The first one is Laboratory for Advanced Combustion and Energy Research. Professor Axelbaum leads that. And again, throughout this meeting, there are posters outside. You'll be able to learn about the research. And again, relating to my first cartoon, the different steps of the pathway you can allude to. My own lab, the Aerosol and Air Quality Research Lab, where we delve on both sides of the coin. Then Aerosol Impact Research Laboratory, which Rajan is just setting up. And then Capita, Rudy Husar, I think, is online. The Center for Air Pollution Impact Trends Analysis, now going really to the global scale, relying on satellites to map out these particles and literally tracking plumes as they move across the globe. The Interface Research Group, which Elijah Thimpson is setting up. The Air Quality Laboratory, Jay Turner, where he looks more at the sort of mesoscale, regional scale impacts of different aerosols. Atmospheric Chemistry and Technology Lab that Brent leads. And then the Micro and Nanophotonics Laboratory, which Lan Yang from Electrical Engineering works with, and some very interesting aerosol problems. There are many other faculty in chemistry, physics. I list some of them, of course. They're all collaborating with us. The outreach sort of spreads beyond this group. Of course, we collaborate with several colleagues in the United States. I haven't listed all of them, but highlight the international collaborations. The university has a fabulous 29 university network, we being the only one in the US, that the Chancellor, Mark Wrighton, who's also a very big supporter of our research efforts, has set up. And as you can see, several of those universities have aerosol groups. And I list again some of them where we have very active collaborations, right? All the way from Thailand, China, India, Korea, and so forth. And some of the names might be familiar, aerosol scientists who have also received their education here and now doing extremely well at their home universities. Another collaborator that we reach out to is the industry. They actually sponsor our efforts, sometimes in a very large manner. And again, you'll get a sort of sprinkling of the activities that we do in a collaborative manner. The coal companies that are headquartered here, Boeing, which has a large defense unit, Cabot, Corning, and there are some of their researchers in the audience today. And then, of course, the national laboratories, which bring their facilities to bear. So Argonne National Labs with their scattering facilities, which many of our students travel and use, and even the other national labs, as I mentioned, other universities, and of course, federal agencies as primary sponsors. Fabulous facilities as we are in the early stages. We are trying to build up a good facility base, and again, there will be laboratory tours, so you would hopefully get sort of some idea of what is going on. We try to say that these are multi-scalar, so I might start from the cluster phase of measuring in a small burner, but then all the way to some pilot scale facilities. These on the right hand side, you can see a combustor where we could, it's also a research facility, do things like oxy-fuel combustion. There are pressurized combustors, next generation combustors, which are being designed. And then here I show a nice instrument that Juan has developed, which we put to use to measure small clusters. A lot of materials characterization facilities and so forth. So again, hopefully you get a sprinkling of an idea of what we have here. There's also an education network. Our students are our biggest resource. We hope to train them well through, of course, regular classes. There are some very nice series of aerosol classes that we teach. We would like to do workshops like this on specialized topics. And through the international network, we really have this cloud that we have set up. We want to, of course, collaborate with our national association and maybe also other international associations where multiple faculty could develop content. And we've set up this system where 2 faculty members are getting together and trying to develop content, and then, of course, deliver that content in their home institutions and also make it available to others who might be interested. So many interesting things beyond just research, but sort of the broader impacts of research being disseminated. I can't, of course, discuss all the projects we have, but you can read the list again, and I just highlighted some. We also collaborate, of course. So many of these projects, there are 2 or 3 of us working together. On the right-hand side, again, I show some nice cluster measurements in flame aerosol reactor, where the interest was to make a doped component. And these initial stages of formation and understanding that is extremely important in, of course, eventually ending up with a known composition or a multi-component material. And while most of it is empirically done today, we hope to, of course, bring the science in to really custom design particles. And then some novel instruments like coupling aerosol mass spectrometers with TAG, thermo aerosol gas chromatography systems, where you want to map out the composition in flight, for example, as combustion is taking place, and so forth in reacting systems. And there's, of course, a multitude of these aerosol reactors we bring to bear. Furnace systems where I can control the temperature profiles. I can use it to make materials, again, for, let's say, environmental sensing applications, or to inactivate bioaerosols. I can study flame reactors. Of course, the same flame system, I could look at alternate fuels, or I could look at the synthesis of cluster dense materials, right? So under what scenarios can the same flame system give me different kinds of particulate structures? And then, of course, these plasma reactors. Actually, here this you can make single nanocrystals, very precise, controlled shape, again, to enable a series of different applications. And this is some of the climate and atmospheric aerosol research. I like this depiction done by Brent Williams, where he's an artist too. So he drew this out himself, starting with the sources, biogenic sources, if you look carefully, trees giving out precursors, bringing instrumentation to bear, now also going into the field systems, right? Do laboratory studies like the reactor in the picture below, where you might study photochemical reactions, but then also going out to the field and then coupling with theory, coming back to the lab to understand interesting problems. And then on the right-hand side, again, some work. People might think that lead has now been removed from our fuel matrix. Of course, for automobiles, that's correct. But airplanes, that's not quite the case. And this is Jay Turner's studies in an airport environment, looking at lead concentrations and the impact in the vicinity, and also, of course, impacts on climate and so forth. A lot of studies. My last slide, I'll sort of conclude here, are our students. Many of them are sitting at the back. They have been key in really organizing this meeting, especially in the short turnaround. And they have a happy hour. Maybe some of you could come back when they have their happy hour once a month. And we picked on our faculty to talk about perspectives and legacy. We don't call it the last lecture in some sense. It's just perspectives and legacy. Rudy Husar, of course, just gave this picture, is when the group got together, and it was fascinating to hear his exploits and meeting Nikolai Fuchs in Siberia, I think in some remote area where people didn't have much access to. And then also his fascinating work where a group of scientists came together, I think, 40 years ago to study, or 30 years ago to study, 40 years ago to study the Los Angeles smog problem. So hopefully you get a good flavor of this in the next 2 days, and we'll now move on. We'll get on to our sessions now. Okay, we'll just continue. We want to keep this sort of informal. Everyone knows each other. We prepared a nice booklet so you can read about the accomplishments and bio sketches of each of the speakers. So just to set the ball, I'll just introduce by name the speaker and their institution they come from. And I hope that's fine. I think everyone knows each other here. The focus would be on the presentations and discussion. So we are honored to have Rick Flagan here. He comes from California Institute of Technology. Rick is, of course, well known, and he will get the ball rolling. As Rajan said, we will have a presentation as Rick's is a keynote, sort of lead-in presentation. We will take some questions after it, but then go into the mode that Rajan described. So